this is one of the bigger things that you'll need to be studying for. Let's go ahead and get started. Alright, so before we actually talk about spanning tree, I want to talk a little bit about why spanning tree is necessary. At the bottom here, we have a computer that generates a broadcast packet, and you can see the arrow there on the bottom outlined with a 1. Now we have two switches that are connected to this particular host, and those switches are also connected on the other side to two Ethernet ports. So we have a redundant loop here in the network, and redundancy is a feature that a lot of networks actually need. For example, like you can imagine a hospital might want to have something like this. Now what happens is these broadcast packets, these broadcast frames, go to each of these two switches, and each of these two switches actually flood those broadcast frames, as you might expect from the switching algorithms we've talked about before, and that's what 2 and 3 arrows illustrate. So what happens is these broadcast frames get flooded across the link, and each of these switches sees the other switch's broadcast frame and floods it back out, and that's what 4 and 5 are. And these frames will actually continue to do this indefinitely. Because there's no real expiration date on frames. The frames will just continue the cycle until either one of those cables is disconnected or one of the switches is powered down. Obviously, this would present a huge problem in an actual live network, and if you introduce more than just 2 switches into a network like this, you end up having issues with broadcast storms just completely taking over networks and making links unusable. And so our goal with spanning tree is basically to provide layer 2 loop detection. That is, we want to eliminate layer 2 loops, and this will eliminate these broadcast storms, as was illustrated on the previous slide. Now, this also prevents frames from being forwarded on redundant interfaces, and what's known as basically ARP, or a MAC address table corruption. What happens is one host will send a frame, and that frame will be flooded by one switch, and another switch might possibly see that frame on more than one interface, and so that host will look like it is on one link, and then a different link, and then a different link, and it'll go back and forth like that. The idea behind spanning tree is that it accommodates link failure, so we allow these loops physically, and we eliminate them temporarily, but let's say a loop fails, we may want to, or let's say a link fails, we may want to bring the other portion of that loop back up. So spanning tree allows that with an okay convergence time. So now we need to discuss the basic building blocks of BPDU, of spanning tree. The basic building block would be called the Bridge Protocol Data Unit, that is the BPDU. Now this BPDU is used to communicate between switches running spanning tree protocol. The idea is that there are 4 primary fields. So you have the root bridge ID, and we'll talk a little bit more about what the root bridge is here in a bit. We have the sender bridge ID. So this is going to be the bridge ID of the switch or bridge that is sending this BPDU. We have the cost to reach root. Again, we'll be discussing cost here momentarily. And you have the hello and max age and forward delay timers that are coming from the root switch. Now this bridge ID, I've mentioned bridge ID a couple times now. This bridge ID is composed of 2 parts. It consists of a priority, which is 2 bytes long, and then it's also composed of a system ID that is 6 bytes long, and normally this would just be the switch's MAC address, although you can administer either of these fields. So first off, we need to determine the root switch. Effectively, what the root switch is it is the center of the hub of your layer 2 topology. So it is the switch that all other switches connect to. It is the center of the universe with respect to layer 2. And all other switches must find a path back to the root and eliminate any other redundant path as a result. So the first thing we have to do is determine what that root switch is, and this is actually a fairly simple process. The switches inspect all of the BPDUs received and look at the bridge ID of all of those BPDUs. The switch with the lowest priority value is automatically selected as the root switch. So in other words, if the switch receives a BPDU with a lower priority, it will automatically select that switch as root. Now, let's say that all of the BPDUs received have the same priority. In this case, the switch with the lowest system ID, or the lowest MAC address in most cases, will be elected as the root. Again, in both of these cases, lower is better. This lowest first system, unfortunately, has an interesting consequence, since most vendors allocate MAC addresses sequentially. For example, one of the organizationally unique identifiers for Cisco is 00000C. And this is obviously one of the very lowest MAC addresses that's even possible. There are only 12 MAC addresses that are actually lower than that, 12 OUIs that you will see that are actually lower than that. And so statistically speaking, this Cisco switch is very, very likely to become root if the priority is not changed now. since vendors tend to allocate their MAC addresses sequentially, 00000C, and then the lower values will all tend to be become root. They will tend to be, because they have a lower value, root switches, even though these switches may be older. Again, these MAC addresses are usually allocated sequentially. And so what happens is in default networks, and networks where no configuration has been done, the tendency is that the lower MAC addresses will become, that is, the older switches will become the root switches. And this is usually a very bad thing because older switches tend to have worse hardware, they tend to have lower performance capabilities, and so forth. And so we don't want inadvertently an older switch to become the root, and so we have to either change the bridge ID, which usually isn't recommended, or we can change the priority, which is a lot easier and makes more sense. So we've elected the root switch, and now we're going to actually start eliminating these layer 2 loops. So the root switch is elected. The second thing that's done is that the non-root switches look at which interface has the lowest cost to get to the root. This cost is determined as the BPDU comes in. A switch will add the interface cost, which is determined by its bandwidth, to the existing cost of the BPDU. And so we're looking at the interface that has the lowest cost to root. Again, the root is the center of our spanning tree topology. And then after that, on each Ethernet segment, the switch with the lowest cost to root will be called the designated bridge. So on each Ethernet segment, we're going to look at the BPDU cost, and the port that ends up receiving the BPDU with the lowest cost will be selected as the designated port, and this port is placed in a forwarding state as well. And so what happens is, if a switch receives no BPDUs on a port, it will place this into a forwarding state because it sees its own BPDU as the best BPDU for that interface. If it receives another better BPDU, it will do this last thing here. It will place that port into a blocking state because the other side obviously has a better cost to the root. And if a switch is root, its BPDU on the interface is going to be better than any other possible BPDU it can receive, and so it will place all of its interfaces into a forwarding state. It will basically make all of the interfaces designated ports. Again, it compares not just the BPDUs received, but also the BPDU generated on that interface. So here we have a simple example of spanning tree topology, and if you look at this diagram, you'll see each of the switches is represented by a little rectangle with a number inside. That number would be the spanning tree priority value, and each of the Ethernet links between these are represented by a little cloud. And so you can see that that cloud A might be an Ethernet cable connecting switch 3 and switch 24 there, whereas that cloud B might be an Ethernet hub that's connecting those 3 switches there on the right. And so when we're looking at this topology, the first thing we want to do is select which switch is the root switch. Just by quickly glancing over all of the values, you've probably already determined that the root switch is switch number 3. So switch 3 will become the center of this particular spanning tree universe. Now, we look at each of the switches that is not root, and we say, okay, what interface is going to have the lowest cost to root? We'll assume, for the sake of this particular scenario, that all interfaces have the same cost. And so if we look at switch 24, for example, switch 24 there on the left, the incoming port will have a cost. Let's say each interface has a cost of 1. The port that is connected to segment A will have a root cost of 1. The port that is connected to segment D will have a root cost of 1, 2, it looks like it's 2 hops away. And then the port that is connected to segment C will have a root cost of at least 1, 2, 3, 4. And so the lowest cost to root is obviously on that little port that's connected to A, and so the interface facing A would be designated the root port. Now we'll look at interfaces D and C. If you look at interface D, it looks like switch number 92 actually has a lower cost, or switch 92 and switch 24 have the same cost to root. So this presents an interesting scenario. Obviously what will happen in this case is the lower priority switch will take effect, and so switch 24 will become the designated port for that particular scenario. And again, looking at segment C, 24 versus 4, 24 has the lower cost to root, whereas switch 4 has a cost of at least 3. Switch 24 will become the designated port for that particular segment. And so if we go to the next slide, we'll have a look at the final scenario. And again, just like I've described, if you look at switch 24, you'll see that the root port has been selected on segment A, and segments D and C have both been selected as designated ports, since that those interfaces have a lower cost to root, or in the case of segment D, the switch has a lower priority. Now we need to discuss some of the BPDU timers. Originally, spanning tree was implemented in networks where link failure may not be detected. That is, you may have a set of switches or a set of bridges that are connected to a hub, and so the physical state of the link does not necessarily reflect whether or not any other bridges are connected to that link. And so spanning tree in its old days relied a lot on timers, and we're going to look at some of those timers now. By default, STP hellos are sent and expected every 2 seconds. In other words, what will happen in a typical spanning tree topology is that the root bridge will generate a spanning tree hello, and that hello will get flooded all the way down to the very, very ends of the network, adding interface costs and so on as they're flooded right along. Now, the max age timer determines how long a switch takes to act on a lost hello. In other words, this basically determines how long it takes to recognize that another switch or another bridge has gone down. By default, this is 10 times the hello timer, or 20 seconds. And so what will happen is if a bridge or a switch does not see a BPDU from the root in 20 seconds, this max age timer will expire, and it will start placing all of its ports into a different state. And we'll talk about those port states here in a bit. The forward delay timer determines how long an interface takes to transition from a block state to a forwarding state. The default for this is 15 seconds, and there are a couple different states that it has to go through that rely on this forward delay timer. We'll talk about those as well. So now we need to see what happens when a link failure occurs. So normally, in a topology where link failure or link detection isn't necessarily available, the only sign that a link has failed will be it will stop receiving STP hellos from the root. And so after the max age timer expires, these block ports are placed in an intermediate listening state. And the point of this listening state is for the switch to determine whether or not there are any better BPDUs on other interfaces. And so in the course of this listening state, which takes 15 seconds, it's determined by the forward delay timer, it will try to pick out the better port, a new root port if necessary, or possibly a better designated port. After the timer expires, all of the non-blocked ports are placed in a learning state, and so the listening state determines whether or not a port is going to be blocked. If a port is not blocked, it goes into a learning state. And what happens in this learning state is no traffic is forwarded out the interfaces, but MAC addresses that are received on those interfaces are learned and stored in the MAC address table. And then the forward delay timer is set again, and so you have 15 seconds from the listening state, and you have another 15 seconds in the learning state. This is in addition, of course, to the max age timer of 20 seconds. After this, the forward delay timer expires a second time, the interface is placed in the forwarding state, traffic is brought up, the better BPDUs have been received, and the spanning tree network topology is reconverged once again. And so if you add up the 20 seconds and the two 15-second timers, we end up with this convergence time of about 50 seconds, and obviously this is a very long time in modern networks.